This video introduces the concepts of roots and radicals. We will first consider square roots. A square root of the real number a is a number b for which a equals b squared. Essentially, a square root of a is any number that squares to a. The principal square root of a is the unique non-negative square root of a. The principal square root of a is denoted by a under a radical sign, sometimes pronounced root a or square root a. The root symbol is called a radical sign, and the quantity under the radical sign is called the radicand. We will need to be careful with the notational details. The use of the principal square root sign is sometimes a bit tricky at first. Both 2 and negative 2 are square roots of 4 because 2 squared equals 4 and minus 2 squared equals 4. However, the square root of 4 equals 2 because we're using the square root symbol. Similarly, the equation x squared equal 4 produces two solutions, namely plus and minus 2. But computing the square root of 4 produces only one value. Now let's consider a few examples. The principal square root of 16 equals 4, since 4 squares to 16 and 4 is non-negative. Recall that greater than or equal to 0 is exactly the definition of non-negative. The principal square root of 25 equals 5, since 5 squared is 25 and 5 is non-negative. The square root of 0 equals 0, since 0 squared equals 0 and 0 is non-negative. The square root of negative 81 is not a real number, since x squared equals negative 81 has no real solutions. In general, negative quantities have no real square roots. The square root of x squared equals absolute value x, because x may be negative and the principal square root must be non-negative. This is an important fact that we will return to shortly. Let's consider cube roots. The cube root of the real number a is a number b for which b cubed equals a. The radical sign for a cube root has a small 3 indicating that the index and exponent is 3. Some examples will help to clarify. The cube root of 8 equals 2, since 2 cubed to 8. Similarly, the cube root of 27 equals 3, since 3 cubed is 27. The cube root of negative 8 equals negative 2, since negative 2 cubed is negative 8. Notice that we don't have the same requirement for cube roots to be non-negative as we did with square roots. The cube root of the fraction 1 over 64 equals 1/4, since 1/4 cubed is 1 over 64. We can define higher order roots in a manner analogous to square roots and cube roots. Let n denote a natural number, and let a denote any real number. If n is even and a is non-negative, then the nth root of a is the real number b for which b to the n equals a, and b is non-negative. If n is odd and a is any real number, then the nth root of a is the real number b for which b to the n is a. When the index is odd, there is no restriction that the radicand, or the nth root, be non-negative. Let's consider a few examples with higher order radicals. The fourth root of 81 equals 3, since 3 to the fourth equals 81, and 3 is non-negative. The fifth root of 32 equals 2, since 2 to the fifth is 32. The fifth root of negative 243 equals negative 3, since negative 3 raised to the fifth power gives us negative 243. The fourth root of a negative number is not a real number because fourth powers of real numbers are never negative. Finally, we return to the important fact that the square root of x squared is absolute value x. Simplify each expression. The square root of the quantity x minus 1 squared is absolute x minus 1. To simplify the square root of x squared plus 6x plus 9, we first rewrite the radicand as a perfect square, and then use the square root of a perfect square being absolute value. To simplify the square root of 16y to the sixth, we again rewrite the radicand as a perfect square. We need to use the absolute value of 4y cubed because we don't know the sign of y cubed. Similarly, to simplify the square root of 81x to the fourth, we rewrite the radicand as a perfect square. This time, we do know that 9x squared is non-negative, so we can drop the absolute value in the final answer.